All right, should we make a start here?
Yeah, let's go.
All right. Okay, thank you. I'd like to welcome everyone to the 6th webinar of the WCRP Digital Earth Lighthouse Activity webinar series. My name's Catherine de Berg-Day. I'm from the Bureau of Meteorology in Australia, and I'll be one of the moderators for today's event. This webinar series is part of the WCRP Digital Earth Lighthouse activity. The aim of this series is to help maintain more regular and open dialogue between active researchers and users on the development and evaluation of kilometre-scale global and large domain models across the world. We plan to hold seminars every 2 months, spanning a range of groups working on kilometre-scale modelling around the world. And you can find a recording of previous events via the webinar webpage. It's a bit of a mouthful. And I think Huw's going to put something in the chat about that. And also, I imagine if you go to the WCRP webpage, you can find more information there as well. So the focus for today is on the experience of NCMRWF in exploring the grey zone in their model development and evaluation, and the work of Raghav Mapati and colleagues in India. Before we get started, I'll pass on to our other moderator today, Huw Lewis.
And a very warm welcome to everyone from my side. So I'm Huw Lewis from the Met Office in the UK. And just before we introduce today's speakers, just to provide an overview of today's event and how to interact as we go through. So we've got 4 speakers today who are going to present a combined talk, and then we'll wrap up with a Q&A session. So during the talk, please feel free to pose any questions you may have in the Q&A feature at the bottom of the Zoom window. We hope as well you'll be able to upvote with the thumbs up sign in there, and we'll try and work through the questions that are more popular as we go through the Q&A later. We'd ask you if you can please reserve the chat function for any technical issues you may have related to the webinar, and so just a reminder to use the Q&A for the session later. I hope we have a lot of interaction through the chat, and please don't be shy in pushing your questions through as we go. For presenters, we will hopefully leave you in relative peace, but if we're starting to run out of time, we'll give you a heads up with some time to go. As with previous events, we're recording currently, and so we will make this recording available as soon as we can via the WCRP website and share that link with people who have registered. So please feel free to share that on with colleagues in your networks as well.
Thanks, Huw. So now it's my pleasure to introduce today's speakers. They are from the National Centre for Medium Range Weather Forecasting in India, or NCMRWF. This is a centre of excellence in weather and climate modelling operating under the Ministry of Earth Sciences in the Government of India, with a mission of continually advancing and enhancing numerical weather prediction systems. It's one of the global NWP centres focusing on increasing the reliability and accuracy of predictions across India and its neighbouring regions. Raghav, also known as Raghu, leads this 6-kilometre model development project at NCMRWF. Dr. Kondapalli Niranjan specialises in forecast verification, generating new forecast products from operational models. Dr. Thota Mahana specialises in process-oriented diagnostics of NWP models, and Dr. Ashutosh Sinha is a young scientist working on this model development with a focus on global ancillary inputs. And so with that, welcome Raghav, and the floor is yours.
Thank you, Catherine, and thank you, Huw. So I'm Raghu. So as we get started, actually, like our title today actually is NCMRWF's foray into the grey zone. I'm joined here actually with an excellent bunch of people. So before we get started, let me say good morning, good afternoon, and good evening. I'll save the good night actually for the end of this talk. So there we are. So this is roughly our outline. Basically going to introduce a bit about actually like the systems presently at operational at NCMRWF. A brief background actually about grey zone. I mean, I don't need to preach the choir here because everybody here should be very well aware of actually like the gray zone, much better than us. So, but anyway, I will try to make an effort that actually like timelines actually like the things around. Then we'll be focusing actually on the model development and the experiments that are being done, and then we'll present actually the evaluation or the model performance results, a brief thing about our future plans, and we have a lot of people to thank, right from Met Office actually, which has been helping us, along with people who really initiated this model development actually. So there we are, and then we should actually have sufficient time for Q&A, I hope. So roughly speaking, what you see here, what you see here actually are the various based actually like systems that we run actually at NCMRWF. We also run GFS systems here, and we do the entire data assimilation, and we also we generate the initial conditions for these models, and all downstream models that our sister organizations make use of it. On your extreme right, you have experiment. I mean, we have actually like something called as an extended range model. Then there's ensemble prediction. We are one of the few that comes up with actually a very high resolution 12-kilometer global ensemble. Then we have a global model, and in these three sort of gray boxes actually have your regional models that are actually like running here. So having said that, let's get into the gray zone, or welcome to the twilight zone. So to begin with, Gage in 1979 sort of actually found the evidence for that famous -5/3 slope. It was predominantly based actually on his relation with wind variability in mesoscale models to turbulence theory. And then from then on, actually like Vanguard actually in 2004 identified that actually when the model resolutions are very close to your turbulent length scales in the atmospheric boundary layer theory, then you have something sort of actually called as terra incognita. And this roughly, I have taken it, this particular figure from his particular paper, the 2004 paper. So you on the left side, you have actually your mesoscale limit, and on the right side, you have your large eddy simulators. So in between them actually is a terra incognita zone, and we are talking actually like models whose resolutions are in this particular zone here. Thanks to modern development, or rather advances actually in computational uh, uh, computing actually HPC, we seem to actually like are in a position to run actually like bit complex and high resolution models. So we need to get into that particular zone. So we are there. From the zone of terra incognita, we sort of actually like started calling it more actually as a gray zone of turbulence or gray zone of convection. And this became more of a community approach actually. And this I'm taken this actually sort of sentence directly from ONET 2019. And there are lots of actually other papers that have actually like focused more with this particular terminology, gray zone. And then they have actually like started experimenting with various aspects of actually like running models actually in this gray zone scenario. So this is roughly from Ponet's paper, and here Dr. Niranjan here actually, who is an expert actually with model evaluation, will be talking a bit more, and we have he has a paper actually that actually describes or rather evaluates various models in this particular zone using this kind of metric around. Within the gray zone, if we speak of global modeling perspective, there are, I mean, I have come across actually various researchers, and I have kept only a handful here, right from Maladel, Nils Vedi, and Peter Dubin, Sato. So there's a whole community that has actually like has been pioneered by these people around. So we are actually like sort of following them in this particular aspect. From a regional model a regional modeling point of view, there's a very good review actually by Prain et al. And within NCMRWF, Dr. Ashim again here actually did experiment with actually explicit convection scheme in regional models around. And then we have Dr. Niranjan's paper here also. And on a grander scheme of things, programs like Diamond, the K-Scale project, GX, Gray Zone project at all, these are all sort of a good forum to really understand actually like various processes actually by using these kind of high resolution models. And we would really like to be actually part of this particular fora actually. Okay. So having said that, actually a bit of a very diluted actually background to Gray Zone, let me talk something more about our model development. A brief background actually, we started this actually in 2019. It was primarily we thought actually like we should explore the options of actually like halving, I mean, taking our existing operational model resolution, which is at 12 kilometer, to half of that, so to about 6 kilometer. So we had the computational resources at the time, and then we thought actually we should be thinking about this in future. So the development of this particular 6 kilometer model was initiated by one of our former heads, Dr. Ian Rajagopal. The development continued actually his success, with his successor, Dr. A.K. Mitra. There were a lot of science enhancements and evaluations. And then our present head, actually, Dr. V.S. Prasad, initiated operational feasibility test sort of actually like wherein can we run this actually given our operational setup? Can we run this extremely computationally expensive resource? Can we do this operationally? Can we sustain this actually for an entire monsoon season and run it live? So we sort of actually like ticked off few of these things. And we started actually like developing a benchmark data set for year monsoon year 2022. And we ran it again live for 2023. So today we are going to talk a bit more actually like more results from this 2023 on this. And having given this background, as most of you may know or might, there is actually a huge consortium actually. These days it's called Access. I mean, since April 1st, 2024, it's called actually as Momentum Consortium or Partnership. Earlier, it was called actually as Unified Model Partnership or UM Partnership. So NCMRWF is one of the core partners actually in this consortium. So we actually developed a version of UM, Unified Model, called NCAR. That is the NCMRW's UM version, which has its own data assimilation system, which has actually its own other verification system and other things. So it's a end-to-end system that is actually like meant for global thing. And this is based actually on the UM, which is a non-hydrostatic grid point model. So when we talk of UM modeling ecosystem, we have this convention of N1024, N1280. So following the same convention, we started calling the 6 kilometer grid axis N2048E, in the sense that N actually is the total number of grid points that are there actually between say 0 to 80 degrees, 180 degrees actually. So, and that is actually like half your hemisphere, and that is east-west, and then 1.5 N points actually from along the latitudes -90 to +90. So what you totally land up actually is about like 2 times N number of actually like grid points along the east-west and 3072 points actually along the latitude. So it gives a nominal horizontal resolution of about 6 kilometers at the equator. The last, that E over there in the end, actually that indicates the dynamical core. This is based actually on something called as even newer dynamics for general atmosphere modeling of the environment, the end game. So the end game actually core is a semi-Lagrangian advection scheme and uses actually a semi-implicit time stepping to solve this compressible non-hydrostatic equations of motion over a sphere. Vertically, it has got same 70 levels actually as our operational model. So 70 levels up to the height of actually 80 kilometers. And there's lot of info actually that can be made available and readily available actually on our website, NCMRWF website. I'm particularly referring to two model developments over here with NCOMG, that is by Sumit Kumar et al. There's a 2018 technical report, and there's a 2020 technical report that deals with actually like various versions of this. So having said that, we started off this first actually with grid generation. Any particular model actually has to start off with actually the basic grid. So our basic orographic grid actually at this N2048E resolution was generated from Globe 30 dataset. So it's a global orography at 30 arc seconds. Spatially, it nominally makes about like 990 meters or almost a kilometer at equator. And we decided to do this entire project actually in a relatively novel way. We made use of something called as ANTS. ANTS is actually, again, a part of actually like a project actually through this consortium or our partnership. ANTS basically is meant for ancillary tools and suites. And it's a software toolkit which is written in a Pythonic way. You basically make use of ANTS to produce ancillaries for any new domain that you might create, or any new set of ancillaries for a new data set that you would actually want to have. For example, tomorrow I have a new satellite data and I would like to make use of the data. Then I would actually make use of ANTS as a way to actually generate the ancillary fields and the files with that particular data set. And you could also derive actually new set of ancillaries if you have a new parameterization scheme. So all this actually altogether, actually the package as ANTS as a package is a very novel and very upcoming actually thing. And it was designed to replace actually a legacy program called Central Ancillary Program at UK Met Office. So there's a lot actually like ANTS is still under a lot of evolution and a lot of development is happening. I was actually like a bit fortunate enough to actually like have a learning actually with Dr. Jamie Kettleborough actually at that time, who was leading this particular project. Right now it is led by Adrian Locke at I guess at Met Office. And I also learned quite a lot actually from Harold Dyson and Carvin Pele, who was actually like leading this development at the time. So a lot of my troubleshooting issues were resolved by them. So huge thanks out. I mean, I should out call out actually for that. And having said that, this is on the left-hand side. What you see is actually a globe data set. For those who are in the community and this one, you might recognize this actually as the standard XCONV. So yeah, it's a very quick way to visualize actually your data around. So for lack of time, I feel that this is much better way to do things. So on the left-hand side, you have your a kilometer globe 30 actually like basic data set, from which we regraded actually to the 6 kilometer data set. So as you can see, in reality, actually like if you look at this, the maximum actually elevation in the original data set is about like 8,750 meters, almost 8.7 kilometers, which represents the Himalayas. But once you take it actually to a regrading thing in our model, so it's not the reality is sort of smoothened out. So those are the things that which we can actually notice outrightly. So we went ahead with this model development, and within, if you look at it actually South Asia in bit more in detail, with this particular orography, there is a very good detail that actually like pops up. So it's a very good representation of orography. We hope that actually like this particular orography will actually help us in resolving many things. So we'll start at going ahead with this actually development further. Then orography is not the only thing. At this point, just let me get actually tangential to this. for those for people who are not familiar with the or this kind of framework, ancillaries are a way to get your external data actually into your model environment. And within actually, you have a hierarchy of this particular information, that external information that can be brought in. And I have adapted this from Huw's tutorial actually on CAP. So at the bottom, or the most important thing that defines the grid and everything actually around, is actually the land sea mask. And next comes your model orography, soil parameters, the vegetation, soil moisture, SST and ice climatologies. And I have not kept actually like highlighted the ozone and aerosols here. So they're all are very, very important. So if you want to develop actually a model, the first and basic thing actually would require within this framework would be the land sea mask and the orography. Then you can keep on actually adding the complexities as you go by. So that is the rough incremental way of actually doing it. So in this our particular approach, we had a slightly different approach than actually the generating the land sea mask and then the orography and the soil. So what we did actually was that first we developed the model orography to a 6-kilometer grid, and then we started generating the land sea mask. The reason behind this approach was that this kind of issue. If you look at the model, most of even our operational model actually has this. There's a land and there's sea. There's nothing actually like various inland lakes and actually like small islands are sort of actually removed from your thing, because at 12 kilometers they might not be a representative of land. So they might be considered actually as a sea point actually. So that's the reason why there's a lot of actually like smoothing of reality, or trying to tone down the reality of the real world. So when we have such a situation, the land points and the sea points are in a binary way, we landed up actually having model issues where the model is expecting a certain kind of number of land points, while our particular orography was giving us quite a lot of things. So there was a mismatch. So we went ahead actually and made a land sea mask actually based on our 12-kilometer existing land sea mask, regraded it actually with to a 6-kilometer using generated uh, grid, 6-kilometer orographic grid actually as a target. So in ants, what you can do actually is that you can have a target grid and you have a source grid. That is, target grid is where the resolution I want to get to, or what sort of grid I want to achieve. And source is actually whatever my source is in. So using actually various regrading schemes, so we can do that. So you set this orography initially as a target point, a target grid, and get your land sea mass that was already there actually at 12 kilometer onto this particular grid. Once we have done that, then we went back actually and got the remaining ancillaries, making use of this land sea mask as the new target grid. So that's how this particular ancillaries were generated. So they were generated actually in a very bespoke manner. While this was all done actually at way back in 2019, 2020. Now we have a rethinking on this, because when we are trying to move to upgrade the model to a different physics and a different thing, we thought that we should actually have a common scenario. I think QE and other things, or we can take this offline actually how this particular thing is done. So we are going ahead actually with a suite-based or a workflow-based approach now. So having said that, having generated actually a basic model grid and other things, one needs actually a suite or a workflow to get started. And that's where actually like we thought actually it's better very quickly, because we started this entirely from an operational point of view. So we basically looked actually at a PS43. Okay, for all those who are not coming from this background, we have a lot of jargon here. So I have not kept a slide actually highlighting this technical jargon around. PS43 basically stands for a parallel suite, which is operational suite. So we basically made use of that, and which actually was making use of a version, actually version 10.8, and the model science configuration was actually like based on GS7. And you basically update actually the entire suite with doing this. I had a bit of actually like difficulties, and they were troubleshooted by my colleagues actually over here, Dr. Jay Kumar and Sumit here. So after that configuration was set up, we experimented with various time zones and other things. And then finally, we thought that actually like let's be frugal in making use of our computing nodes. So finally, we arrived actually at a 3-minute time step, which was actually very feasible. And we could do it actually just by making use of 174 nodes on our operational system. So once we have done that, then we had our sort of a bingo moment, and this was our first simulation actually that points to 2020 September 14th. So this is how things were. And having said that, I'll just now that the model is ready, I'll just pass it on actually to a young colleague of mine actually who has been experimenting with this particular model with his convection schemes around. So I'll pass it on to Ashutosh here.
Thank you. So talk will be on the convections in this 6-kilometer model. So there are basically two types of convection schemes present there in the 6-kilometer model, which is this 5-way convection scheme, which includes the mass flux scheme plus turbulent schemes, and this is the 6 convection schemes. This 5-way convection scheme is basically a basic parameterization approach to model the convective processes. This is the simple representation of this convection scheme. By talking about the efficiency, we see that this scheme is computationally less intensive and making it suitable for certain types of simulations which are where the computational resources are constrained. While this 6-way convection scheme, where we see that this is similar to the 5-way convection schemes. However, there are some revisions made in this 6-way convection schemes which are to sort out the problems which were present in the 5-way version. This 6-way scheme is more advanced and detailed representation of the convection. This has improved physics, like the physical processes, the interactions, and providing a more accurate simulation of the convective events. But this 6-way convection scheme needs high computational resources. So for running this 6-way convection scheme, we need more computational resources. So moving next, this 6-kilometer model which we are running is having this 5-way convection schemes due to some computational constraints also, which is largely based on the Gregory and Roundtree. There are basically 3 types of convections in this 6-kilometer. Which the first is the shallow convections, which starts from the boundary layer. Second is the deep convection, which also starts from the boundary layer, but not diagnosed as the shallow convections. The mid-level convections starts above the boundary layer and or above the shallow or deep convections. So why we are switching? Why we are doing this switching of experiments? So while going through different literatures, we find that many studies supported the fact that the resolving that deep convection explicitly this can help in benefiting the model accuracy. Like this was done by Vedi in 2022. 2020. Also, there are many studies which are which use explicit convections, which have been globally carried out, such as Clark and Tomasini. Basically, we are in the same boat as the Met Office, so our convection schemes and this protocols are slightly similar to them also. and why this was done for this 6-kilometer model. So we see that this 6-kilometer, which is a higher resolution, is still untested in its capacity to resolve the gray zone issues, or can it run the this model without a convection schemes parameterization, or we can see what are its performances, as how it can resolve the rainfall explicitly. And there we defined a small convection permitting experiments. So basically we defined 3 sets of experiments where we see that how the initial performance of this 6-kilometer model in rainfall simulation is carried out. Also, we need to note that the 6-kilometer is being run with the operational dumps from the 12-kilometer model. So a date has been picked up, that is 1st July 2023. So we are basically planning for more runs for the complete July phases, so that we have a good record of how this explicit convections or switching of the deep convections can help in model performances. First is the control experiment, which is run with the parameterized convection which is including all the three convections types which I discussed earlier, that is shallow, mid, and deep convections. Second is the deep convections have been switched off, that is basically denoted as deep off. Here we have switched off the deep convections, but we have allowed the shallow and mid convections to occur in the model. And lastly is the explicit convection, which where we are completely switching off the convections, that deep, mid, and shallow convection. All these are being switched off. So this the next slides will be discussing some initial results that in terms of the total rainfall and convective rainfall. So in 3 sets of experiment have been done with total rainfall as control, deep off, and explicit, while the convective rainfall is being discussed with control and deep convections being switched off. These are some initial results. That is for the first day, 1st July 2023. The first figure is the GPM rainfall, which is the observation. Second, we see that the control run of the in the total rainfall and 6-kilometer is quite similar to the GPM. At some places we see more rainfall. However, mostly we see some less rainfall than the GPM at some location, like mid latitudes in southern hemisphere. This third figure shows the bias in between the control and GPM rainfall. So here we see that the central latitudes have this region of Central Pacific is having wet bias, while the maritime continents and this monsoonal regions have some mixed signals, like we see blue patches here over the Bay of Bengal region. The Central Africa is also having wet bias. So in southern hemisphere we see some mid latitudes with some mixed signals, as the southern Pacific, Atlantic have some positive biases, while in near the Australian regions we see some deficiency in the rainfall. So these two figures show the first figure is the convective rainfall, which is in the control experiment, and this is being followed by this F number is this 6 kilometer convective rainfall, which is being subtracted from the GPM, and here we see the biases as how the convective rainfall have been occurring here. So here over these central latitudes, the ITC regions we see western regions with positive biases, while the maritime continents and the Bay of Bengal regions having this negative biases. In southern hemisphere also we see less rainfall than the GPM. Here the next figure is the deep convection trough. Here we see some irregular patches of the rainfall distributed. So switching of the deep convections leads to the deficiency in the rainfall also. So over the equatorial regions we see some good rainfall occurring over here, but the biases in comparison to the GPM we see with dry biases over most of the equatorial regions. While this Pacific Ocean regions are having positive biases, southern hemisphere is having dry biases. So coming to the total rainfall in with deep convections being switched off, we see similar features as the oceanic regions are having some positive biases, while the land regions like the African continent, the Indian subcontinent having some mixed signals, and the most of the maritime continents are having dry biases. Here in southern hemisphere also we see some mixed signals. So and coming the last one is the receipt convection, where all the convections have been switched off. So here we see rainfall mostly confined over the equatorial belts and the Pacific regions. In southern hemisphere also we see some good rainfall, but the biases in the in the explicit conditions for total rainfall, this show some mixed signals, as most of the cases we are having some wet to dry biases here over the equatorial regions. This is basically the one-day data set for the 1st July 2023. So initially the performance is showing some mixed signals. So more runs are to be carried out for our definite hypothesis that this 6 kilometer can it resolve the convection explicitly over the globe, or in terms of computational cost, we see the operational model which is being run at the center is having is using 22.10 node hour per day, while the control runs which were being shown, they have used 185.39 node hour per day. The deep the deep convection which were switched off, they were using 179.22 nodes per day, and this explicit convection, so least nodes as 158.10 node hour per day. So we see reduction in the use of node hour per day. This show that this 6 kilometer control uses about 8.4 times resources in comparison to the income 12 kilometer which is being operational here. The when you switch off the deep convections, it reduces to 8.1 times per income 12 kilometer, while the explicit conditions we find the least resources as 7.15 times the 12 kilometer operational runs. Basically, we are having more runs to be carried out for in the explicit condition. Then only we can be definite about how the convictions in 6 kilometer can be resolved. And moving next, the Dr. Niranjan will be focusing on the results of performances of this conviction schemes later.
Okay, thanks, Dr. Raghav and Dr. Stosh for elaborate discussion on the history of this model development, 6 kilometer model development. So I just started with some of the gray zone question that was given in the UK Met Office website. So there are several scientific questions and posed in that website. So one of the question I just highlighted, so which we are currently doing with our current operational runs, I mean current experimental runs in the 6 kilometer. So how can the effective resolution of a model be determined, and what is the impact of model numerics on the characteristics of these convective structures? So these are some of the partly we address these questions, and more with more experiments in the near future, we do more answers to get all these questions that are posed in that second phase of this gray zone project. So coming to the first question, so any model, we need to see first the horizontal kinetic energy spectra, which is a basic thing that it is a testimony for the acceptability of the design and configuration of any given NWP model. So the accurately representing this kinetic energy spectra is which is very essential in these models because it helps to establish saturation bonds to the forecasters at various scales. So for example, the right hand side, what you see is a graphic, schematic from the Scamarog, which shows that the kinetic energy spectra has a canonical structure. So the large scales, particularly on the more than 5,000 kilometers, those scales have a shallow structure, and while the synoptic scales, particularly in the hundreds to thousands of kilometers, it has a slope of -3. And while coming into the mesoscales, which is of hundreds of kilometers, it shows a -5/3 slope. So all these things which should are represented by any given NWP model. So these characteristics are observed in many observation analysis, particularly in the aircraft observations by previous many studies. So coming to our spectra. So the global models, we have two, as you already heard from the Dr. Raghav, that we run a lot of operational models, particularly the 12-kilometer run model being run from several years. We recently tested its energy spectra. Along with that, we also tested the 6-kilometer model, how best this 6-kilometer model is representing the canonical energy spectra. The particular the right hand side top, you may see that the paper where we tested all our global and regional models, including this 6-kilometer model. So we showed the initial results are good at 6 kilometer because it is better resolving the mesoscales compared to the 12 kilometers. So what you see is the slope of the spectrum particularly steepens from the tropics to mid polar latitudes, and particularly the tropics have relatively shallow spectrum with a quasi-uniform slope between -3 and but it deviates from the in the mesoscales. While the mid latitudes, we can clearly notice a two-segment spectrum. One that is a canonical -3 slope in the synoptic scale, while -5/3 in the mesoscales. Finally, the polar regions also, I mean, indicates a very good canonical two-segment spectrum. Okay, the fact that the spectral scope differs between three zones is basically consequence of underlying dynamics, because you know that the barotropic things were very important in the tropics, while the baroclinic structures cycles are very Rossby waves associated with these baroclinic structures are more important to determine the spectra in the mid latitudes and polar latitudes. So particularly particularly the convection is also a key to initial growth, whereas these baroclinic processes are lead to higher growth rates in the mid latitude regions. So basically the dynamics underlying the dynamics in the tropics and mid latitudes are crucial for detecting this canonical energy spectra. So as you can notice that we see a good improvement, particularly in the mesoscales in the 6-kilometer model, because the slope is more closer to the -5/3 compared to the compared to the 12-kilometer model. And also the energy also, you can notice that in the mesoscales, it is slightly higher. The mesoscales I have represented in the gray shading. So where you can notice that 6 km is the mesoscale energy is higher and the slope is more closure. And it is also worth, whatever the results, what you show here is a parameter with the parameterized convection. So please notice that. And one more thing, as this question posed in the second phase of this gradient project, how the effective resolution of the model can be determined from these experiments. So here, basically, the effective resolution can be inferred as a dynamical resolution, whereas the nominal resolution, so which is basically a mesh size of the model grid. Suppose you are taking a 12 kilometer, is a 12 kilometer grid. So one of the most revealing feature of this K spectrum are the tails of the spectrum, which you can notice in the right-hand side top, that as you go for higher wave number spectrum, your energy is deviating from the actual slope of minus pi/3. So we can actually derive an effective resolution from this slope. So the slope where it actually deviates from actual minus pi/3 slope can be accepted as an effective resolution, because one of the rationale behind this definition is that the modes with higher wave numbers than the effective resolution are damped relative to its atmospheric structures. That are basically, we can tell that these structures are dynamically, suspicious, because whatever the resolutions you are seeing below the effective resolutions are dynamically suspicious. So we also did the right hand side top below plot. You can actually notice the 6 kilometer model spectra. So we are trying to establish this effective resolution from this model based on the Lindbergh analytical fit, because which is also the analytical solution he brought out in his paper based on the aircraft observations. So what you can notice is that the slope is very minus pi/3 in the synoptic scale, and as you go to the mesoscale, the energy, the kinetic, the rotational as well as the divergent energy is very close to the minus pi/3. But after somewhere around 80 or 90 kilometers, like around 10 to 12 delta x, this energy is deviating from the actual observational spectra. So this is where we thought that probably the effective resolution of our 6 kilometer model. But please note that these are done with the parameterized convection experiments. And one more thing, why we are doing this rotational and divergent spectra is because we need to understand also understand the physics behind the minus pi/3 mesoscale spectra, because a lot of theories already made a concession. All the globally, the minus pi/3 is already accepted. The theory behind the minus pi/3 slope is already accepted. But one of the problem with the minus in the mesoscale region is still it is unresolved. So there are many theories were proposed, particularly the gravity waves released by the convection, and also the upscale type of energy or direct downward cascading of energy are one of the plausible theories behind this mesoscale energy spectra. So that's why we are also trying to understand the reason behind this minus pi/3 spectra in the mesoscales. So let us come to the cloud representation. So as Dr. Ashutosh mentioned some of his results from the experiment. So we also see how the deep convective clouds, particularly in the ITZ band, we see in the top right hand side top panel is from the actual satellite observations, and while below plot is a parameter with the experiment with a parameterized convection. What you can notice on overall, the tropical belt highlights the deep convective clouds linked with ITZ, while in the mid latitudes, both northern and southern hemispheres, we see the slanted cloud bands which are visible, and these are clearly associated with the large scale Ross-Beers, as everybody knows, and those structures are well represented by the model. The large scale features are very well represented by the 6 kilometer model. But what you can notice is that this small scale convective clouds in the ITCZ still it is not able to resolve. So basically, we know that it is a parameterized convection experiment. So hence, so we try to do the several experiments, as Dr. Ashutosh mentioned, like deep convection and mid-level convection. Deep convection off and completely explicit convection experiment. So basically, in the Metaphysics unified model, we have this this convection scheme is based on the mass flux, and it has 3 different layers. The instability is generated at 3 different layers. One is a shallow convection, which is in the triggered in the boundary layer, but and mid-level, where you can notice that that instability is triggered above the boundary layer. So basically the triggering mechanism for the mid-level and deep convection is mostly similar. So what you can actually notice here, the interesting thing is the top right-hand side top below panel. The small scale convective structures within the ITCZ are now clearly able to resolved by the 6-kilometer model. But please also note that because the satellite timestamp and the model timestamps are little different, not much, but it is more than 40 or 1 hour or so. So that's why we can't see the exact match with the convective cloud, but still what you can notice is the small scale convective clones within the ITCZ are clearly able to resolve by the 6-kilometer model. Now the question here comes that is there any improvement in the canonical energy spectra? Now so all these 3 experiments, particularly the explicit experiment and 6-kilometer parameterized convection and 12-kilometer I am showing here. So the mid latitudes as well as for the tropics. So there is a clear 2-segment spectra, particularly in we can notice in the mesoscale region. Even though there is not much significant difference in the mid latitudes, but you can actually appreciate in the tropics, this 6-kilometer explicit convection is very close to the actual theoretical spectra of -5/3 slope in the mesoscale. So this is one of the very important result why we need to move around this low resolution to high resolution, particularly with the explicit convection schemes. Now, coming to even more in detail how this convective thing. So I showed here an example of a torrential rains in the northern India, which happens during 2023 of 10th. So I mean, a lot of people are affected and highways, and there is an extensive damage of power station supplies during this period. So what you can notice is the left-hand side is an inside 3D picture of that particular event. Now, the second one is a control experiment. What you can notice is that there is, even though the model is able to predict this particular feature, but you see that small scale convective structures are not able to resolve in this control experiment. But in the deep convection experiment, even though it is able to resolve, but you see there are a lot of false alarms, particularly in the central India, even in the northern northwestern region. So it is able to resolve, but the problem is a lot of false alarms in the deep convective clouds. While in the experiment, explicit convection in the right hand side, extreme right, you can notice that these type of false sounds are very less in the explicit convection, and model is able to resolve and develop deep convective structures within that, and it is very closely resembling with the actual INSAT 3D picture. Apart from that, we also do some of the scale dependent verification. Yes.
Just to say we have only 5 minutes left in the whole session, so we're gonna have to try and wrap up.
I'm completing almost 1 or 2 slides. So yeah, scale dependent verification also we do, and as you know that high resolution simulations improve the small scale features, but often mismatch the locations and time. This mismatching of location and time is a double penalty issue. So we also do, but what you see the right hand side plot is a control and explicit convection scheme. Now what you can notice is that the purple color indicates useful spatial scale for a particular lead times. Okay, so the model is clearly able to resolve individual convective clouds. The FSS score clearly able to show that the score is very useful score, particularly for the deep convective clouds in the model. Now we also do the scale dependent verification of this particularly rainfall, and you can actually notice that there is a significant improvement. Particularly the maximum rain is in the control is 90 millimeters per day, but whereas you see the observation, sorry, in the explicit convection it is 283, which is close to the observations, like which is 237. So basically the convective clouds, the exact location and the intensity was well represented in the explicit convective experiments. So basically my last slide is this. So we do a lot of verification process at NCMRWF. One is a basic conventional verification system using model evaluation tool, aligning with the Met Office, UK Met Office, and right hand side you see the process oriented diagnostics. A lot of PODs we do, and my colleague Dr. Mohan will present a few of those results. Thanks.
Hello, am I audible?
Yes, you are, Mohan. So yeah. I'm going to suggest that you try and wrap up in maybe a minute or 2, 3 at most, and it will compromise our time for Q&A, I'm afraid, but we will try and hear your work. So please proceed, but we don't have a lot of time.
Okay, yeah, I don't go into the background details. I think I have my colleagues have almost all they have shown the results about 6-kilometer runs. So what my main aim or the main focus at NCMRWF is to see whether the resolvable features in 6 kilometers, whether it is giving for the right reasons. So the question that I'm asking is that whether this kilometer runs can the results that we are seeing is for the right reason. So for that, I'm applying this POD, this is the process under diagnostics. Okay. So can you go for the next slide? I don't know. I'm not able to control the slides.
Raghu, are you able to go? There you go.
Yeah. So what I want to say is that although this is the results that I'm going to show is all the 1 month runs, that is 30 days runs. This is July 2023, which is the parameterized convection, not the explicit, because the samples are very limited to see the process under diagnostics. So what the results that I'm presenting is all with the parameterized convection. So what I have identified is that the 6 kilometer runs, they are as the lead time increases, the biases increases with respect to the observed rainfall. This on the right hand side, you can see the biases with respect to GPM. So at certain regions like equatorial, especially on the western equatorial Indian Ocean, the Bay of Bengal and the parts of land regions of the central India, is showing a very excess moisture or dryness or these regions. So the question is that whether they can affect the equatorial waves and the Kelvin wave, so this equatorial Indian Ocean or the Hadley cell dynamics, that how these things are affecting in 6 kilometers. So go to the next slide. So what I was asking is that do all these regions where I have identified these large biases, I just want to see how these tropical column water vapor, which is considered as a theoretical precipitation, I just want to see how they are aligning with the rainfall or these 6 kilometers with respect to the lead time in the forecast. What I can see is that over land regions, there is a very gradual pickup in the 6 kilometer, which is very consistent with the 12 kilometer operational model. I don't see any incremental changes in the 6 kilometers in the parameters runs. So this could be probably one constraint. And then over the ocean regions, as you move from the land to the ocean regions, this pickup is very steep. That's what we expected. So the gradual the convective transition from the incremental changes in the column water vapor can be seen in the land regions, but they are this quantum jump for the ocean regions, and which is very consistent with the 12 kilometer that results has been published in the recent journal in 2024. Go for the next slide, please. The another POD that we are checking for the parameter runs is the sensitivity of the rainfall with respect to the free tropospheric moisture. Generally, the convection that is strengthened because of the free tropospheric moisture can be seen in the ocean regions where the land and the Bay of Bengal regions, that sensitivity is lost. The ultimate bottom line is that the 6 kilometer runs only over the equatorial Indian Ocean where you have excess moisture, that free tropospheric sensitivity can be seen, but in the central and Bay of Bengal regions, that sensitivity is lost. Over the next slide. So similarly, what I can see that with respect to lead time, if you see the error propagation, that is when you successive forecast, when you subtract the successive forecast with the analysis, you can see that there is a drastic changes in the moisture. The sign of the moisture is changing from positive to negative. Very excessive drainage is seen in the land regions and even the vertical velocity, which is a very large scale field. And then large scale field is a very important parameter for the transport of moisturistic energy, which can be seen that the change in the structure, the tropospheric peak ascent is completely changed to descent in some forecast lead times with respect to forecast lead times, which maybe affects the gross moisture stability when you see the moisturistic energy transfer from lower levels to higher levels, and also affect the Hadley cell dynamics and equatorial waves. Go for the next slide, please. So what we want to do is that the main two regions that we identified is the surface moisture and the vertical velocity. So we want to study the 6 kilometer runs with parameterized convection and explicit convection in two frameworks, which is the moisturistic energy barrier framework and as well as the plume buoyancy framework, which I have shown here. So this is what we want to do in the future, where we expect that the moisture variations in the boundary layer can be more resolved and more identified. The sources for these errors can be identified by using this buoyancy framework. That's all from my side. Thank you.
Okay, thank you all, and thank you to Raghu, to Ashutosh, to Niranjan. And we will give ourselves a minute or two just to touch on perhaps a question that summarizes some of the thoughts from the chat. Can I ask, and in slower time, you can maybe pick up some of the questions from the chat and respond to people individually as well. I guess some uncertainty around the length of your simulations and your initialization strategy. And could I ask a related question on how much are you seeing spin up, or how long is it taking for your high resolution models to spin up from presumably a lower resolution analysis? Have you got any insight on that?
Right. We did actually like a small experiment with that kind of thing, and we noticed actually like it takes almost a day actually, or sometimes half a day for it actually, like for a 6 kilometer to catch up. So when we run it actually in a cyclical mode, it pops up actually down to about an hour. So that's what we have actually in terms of spin up issues. So after an hour, actually, if you do it cyclically, it's fine. I hope I answered the question.
Yeah, thanks. Kat, we probably have time for another question.
All right, I'll ask one quick one. So I was curious, particularly with your rainfall bias plots, whether that was, what lead time those biases were and how many samples were contributing to that bias calculation.
You mean
Yeah,
the spatial biases that you're talking?
Yeah, yeah.
That is
Yeah, I should be.
hello.
Yeah, is
Yeah.
Mohan going to answer
Yeah.
that, or?
I can answer that. The spatial bias that I have showed in for the POD is the 1 month run, that is for July.
Mm-hmm.
That's because of the limited samples. I couldn't go for the other runs because I was concentrating on the 2023 July, where the MJO is very active in 3 and 4 phase. So the biases you can see is the tilting rainfall band, which is expected for that region. That biases is completely seen out from the central India to the maritime continent.
So it's biases across a single run or biases from a single lead time?
It is it's a 3 lead times. So day 1 and day 3 and day 5 have shown.
Okay, cool. Thank you. All right. Well, in the interest of time, I think we'll finish there. So we'd like to thank our panel of speakers again for their excellent presentation and for answering a couple of questions. And many thanks to all of you online for your attendance and participation today in the chat. Hopefully our speakers will be able to answer a few more questions in the chat. And Huw?
And yeah, any feedback on today's event and the series as a whole is very welcome. So you can send through to me directly or to Rosimar Rios-Berrios from NCAR as a co-convener. I'll just flash up a slide in a second with our contact details. And we're also really happy to hear from anybody who wishes to volunteer to give a future seminar. We're just working up plans at the moment for our next event in September, and also looking forward to hearing from Kat's colleagues at the Bureau of Meteorology in Australia later in the year in November. But please do get in touch if you have any, if you wish to contribute to future talks on this series. With that, I think we are just one final thank you from me before we close out to Kat. For stepping in to be a co-convener for today's event to help out with the time zones. And Kat, I'll give you the final words.
Thank you. So we'd also like to inform all registered, we will also inform all registered participants when the recording of today's event is available online. And please also feel free to share that recording with any colleagues in your organisations and networks once it's available, and to encourage them to register for future events as well. So that wraps up our session for today. We'd like to thank Raghav, Niranjan, Ashutosh and Mohan again, and to all their colleagues as well who contributed to this work. Thank you also to Maureen and the WCRP Secretariat for all of your support. And thank you all online for joining, and we look forward to seeing you next time. Thank you.